Thanks for taking the time to watch the first video in our end-to-end testing series. End-to-end testing builds on traditional transmission line protection. So we're going to start with some basic principles from the Relay Testing Handbook series to make sure everyone is on the same page before we delve into the end-to-end testing details in future videos. Power lines transmit energy from one location to another and are the lifeblood of the electrical system. There are many problems that can cause a power line to fail, such as lightning strikes, animals spanning two lines, equipment failure, or just plain human error. Your traditional overcurrent protection worked well when the power flowed in only one direction because the fault can be located by current magnitude. The relay closest to the fault will trip first in a properly coordinated system because of the large current flowing into it and its smaller pickup setting. Current can flow in any direction on an electrical grid, so it's almost impossible to set all of the relays to operate correctly for every possible scenario. Even if you were to achieve the impossible and set every relay perfectly, everything would get thrown out of whack the next time the grid is changed to add a new generator or customer. Imagine that you're a utility design engineer in the dirty 30s, and you keep losing the entire electrical grid for every fault, no matter where it is on the grid. What you really need is a relay that will operate for any fault on the transmission line it's protecting, and ignore faults anywhere else on the grid. You can measure the voltage at any point in the system using PTs. And you can also measure the current entering and leaving the power line with CTs mounted at each end. You can use the current and voltage with your standard electrical formulas to calculate phase current, residual current, phase voltage, residual voltage, directional overcurrent, power, resistance and impedance, any symmetrical component, or differential current. Will any of these values help you determine whether a fault is on the transmission line or not? We already know that overcurrent and voltage elements are not selective enough for this application. Symmetrical components are mostly extensions of current and voltage that are good at identifying what kind of fault occurred, but not where the fault is. Power and directional overcurrent will tell us what direction the fault is, but they're not selective enough to determine if the fault is on the power line or somewhere further down in the system. The perfect solution is differential protection. Differential protection monitors the current entering and leaving the transmission line and sums them together. If the currents cancel each other out, the differential relay will not trip because the system is either operating normally or there's a fault that's not on the transmission line. If the current and voltage leaving the transmission line do not cancel each other out, the fault must be on the transmission line, and the relay will open both circuit breakers. This looks like a great solution. Too bad this is the 1930s, and the technology necessary to transmit three-phase analog signals across large distances in real time doesn't exist. That leaves you with impedance, which is a pretty good second-best solution. In order for this solution to work, you need to know the impedance of the transmission line. You could measure it with fancy equipment, but it's usually easier to calculate it using size of the wire, length of the transmission line, and spacing between wires. Let's imagine that we've run through the calculations, and miraculously, the spacing and type of wire works out to 1 ohm per mile. The transmission line you want to protect is 10 miles long, so the entire impedance of this line is 10 ohms. If we applied a dead short at the end of this line, the relay would measure the voltage and current flowing through the relay, apply Ohm's law, and calculate 10 ohms. If there was a fault 50% down the line, the relay would measure 5 ohms. You've come up with a great solution to the problem that can be applied to any transmission line as long as you can calculate the line impedance. You've gone into your workshop with this information and created an impedance relay that will only look for faults in the forward direction. Your creation has an adjustable pickup system so that you can apply this relay to any transmission line, and now it needs a setting for the 10 ohm power line we started with. What pickup setting in ohms will provide the best protection for this transmission line? Did you choose 10 ohms? That's a great setting for a perfect transmission line in a textbook. Unfortunately, we live in the real world, and there are a couple of problems with a setting set to 100% of the transmission line. The first problem is that we calculated the transmission line impedance, and there will always be errors and assumptions that will affect the calculations. Even if we could account for the inherent inaccuracy with the calculations, the transmission line impedance will change with temperature and spacing between wires. Seasons and wind can change the transmission line impedance. What signals are you using to measure the real-time impedance? Those CTs and PTs aren't perfect, especially the CTs. What is the standard percent error allowable for protection class CTs? If you guessed 10%, you're correct, up to a point. Protection class CTs can have errors up to 20% when the current exceeds 20 times its rating. All of these problems add up, and if we set the impedance protection to be 100% of the transmission line, the real-world impedance may be larger or smaller than our calculations. If the real impedance is smaller than our setting, our relay may trip for a fault on an adjacent power line somewhere else in the system, the very thing we were trying to prevent. Most impedance relays are set to operate instantaneously, with a setting somewhere between 70 to 90% of the line impedance, to make sure that the relay only trips when a fault occurs on the protected line. This protection is usually called the Zone 1 protection. What happens if the fault occurs on the last 30% of the transmission line? You could add another relay to trip at 100% of the line with a time delay, so that if the relay incorrectly detects a fault on an adjacent line, the relay allows the adjacent line relay time to trip first. If the fault is actually on the line, the relay will trip after a short time delay. In fact, you could purposely set the Zone 2 relay to overreach into the other transmission lines in order to provide 100% protection for this transmission line and backup protection for adjacent lines if those relays fail. Most Zone 2 impedance elements are set at 120% of the transmission line they're protecting, with a 15 to 25 cycle delay to allow time for the adjacent relays to trip. Zone 1 and Zone 2 protection overlap and provide 100% protection of the transmission line and backup protection for adjacent lines. Remember that there's another relay on the other side of the transmission line looking in the other direction, and all of these zones overlap to provide a pretty good protection scheme. Any fault in the region where the two Zone 1s overlap will trip both breakers almost instantaneously, and a fault outside that region will be cleared instantaneously on one side, with a maximum time delay of 25 cycles on the other side. Click the subscribe button to get automatic updates whenever we post a new video. The next video in this series will demonstrate this protection scheme in action. If you want more information, check out the description below for links to other videos, the relay testing handbooks that this video is based from, and online training courses. Please like this video if you found it useful. It helps us get noticed, which means that we can afford to keep posting free videos for you.